Hello, welcome to Chapter 4, which is over vector spaces. This is section 4.1, talking about vector spaces and subspaces. At the beginning of this chapter, I was reading it in the very first sentence kind of stood out and it made me kind of giggle a little bit. It said the mathematical seeds planted in chapters 1 and 2 germinate and begin to blossom in this chapter. So I hope that you find that your mathematical knowledge is blossoming as we move through this chapter. This section contains more abstract topics. I think you will find that you will have to spend a little more time in this section really analyzing and thinking about the meaning of different things and how it's used. So just plan accordingly and know that this section is a little bit different than some of the others we've seen. So up to this point, we have thought of vectors as different elements in Rn. And we're going to see some different properties. And we're really going to focus on R2 and R3 in this section. But I want to remind you that Rn is called a vector space, and they could appear to be different, but if you take a closer look, they could be similar, and vice versa. So this is going to be a bit abstract, so just kind of bear with me as we go through this material. So the first thing we have here is the definition of a vector space. And I want to remind you that we will have some set of V with a set of V with different objects called vectors. And we'll have two different operations that we're focusing on, and that's addition and scalar multiplication. So the following properties or axioms are going to be satisfied here. And you can go ahead and pause and read through these. There's no need for me to read them to you. So here, basically, the examples in this section are very, very different. They're not really examples. They're more like statements. It's kind of bizarre. But the spaces in Rn, where n is greater than or equal to 1, are the prime examples of vector spaces. So the geometric intuition developed for R3 is going to help us visualize some concepts throughout the chapter. So I want to refresh your memory here. R3 is a 3x1 column matrix with 3 entries. So like this. And if you're trying to visualize this geometrically, it is basically a 3-dimensional coordinate space. So stuff you may have seen in other classes. So this is example 4 from your book. It's directly from your text. I just copied and pasted it here. But again, these are not necessarily examples, but more like additional statements. But the example here and the next example basically explain the properties or axioms of vector spaces in more detail. So go ahead and pause this and then come back and I'll kind of touch on a couple things. So it talks about the degree of a polynomial, and remember the degree of p in this case is the highest power. So whatever the highest power is. Additionally, if you have like just p of t equals some number like 4, then that is a degree of 0. It's not an exponent necessarily, it's the degree. Let's see, it goes on to say if all the coefficients are 0, then p is called a 0 polynomial. We talk about the sum of vectors and scalar multiples that look like these, and it talks about the different axioms that are satisfied, and that's from that list from the previous couple slides. So since these things are satisfied, then P sub n is a vector space. This type of illustration is used in trend analysis of data, so that's a real life example. This example is very similar to the last. So I think if you go ahead and pause this and read through it, it gives a little more of a concrete example here. And you can go ahead and read through that as well. So now we come to subspaces, and here's the definition of a subspace. So a subspace of a vector is a subset H of V. So I want to remind you of a subset. So the subset H is basically going to be a subset of vectors in this case. So the following properties are going to be satisfied. The 0 vector of V is also in this subset. H is closed under addition, so that means if U and V are in this subset, then U plus V is also in this subset. And the same similar situation for scalar multiplication. H is closed under scalar multiplication. So if U is in the subset, then C times U is also in the subset. So when we talk about subspaces, they are typically used with at least 2 vector spaces in mind, so one inside the other. And if we say that U is a subspace of V, that implies that V is the larger space. Every subspace is a vector space. Conversely, every vector space is a subspace of itself, or possibly a larger space. This is a statement from the book. It says the set consisting of only the 0 vector in a vector space is a subspace. It's just called the 0 subspace and written in this way. So we'll talk a little bit more about subspaces, and here's another one of those fancy examples directly from the text. So basically this is saying P is the set of all polynomials. They have real coefficients in operations. So P is a subspace of all the real values, real valued functions in R, the set of real numbers. And you can go ahead and read through that a little bit. So here is your first legitimate example, I would say. And it's even not super legitimate because I'm just going to kind of talk you through this. So you may need to pause it and rewind if needed. But the first thing that this says, and you might need a little bit of time to wrap your head around it, is it says that the vector space R2 is not a subspace of R3 because R2 is not even a subset of R3. It goes on to say that the vectors in R3 all have 3 entries, whereas the vectors in R2 only have 2. So before I go on, I want to kind of explain this a little bit further. Recall that R2 is the set of vectors AB such that A and B are in the reals. On the other hand, R3 is the set of vectors ABC such that A, B, and C are in the set of reals. So this tells me that R2 is not even a subset of R3 because these two items represent different types of geometric objects. R2 does not contain anything in R3 because R2 is the set of ordered pairs, whereas R3 is the set of ordered triples. So it may look like it and act like it, but it is not a subspace. So going on now, and again, you may need to wrap your head around that because it's pretty abstract. So we go on, and the set H is given by this vector here such that S and T are real. It is a subset of R3 that looks and acts like R2. However, it is different than R2. So what we want to do is we want to show that H is in fact a subspace of R3. And this is where I'm just going to kind of talk you through this answer. So the 0 vector is in H, and H is closed under addition and scalar multiplication because these operations on vectors in H always produce vectors whose third entry is 0, which belongs to H. So H is a subspace of R3. Go ahead and rewind that and go through it again if needed. The term linear combination refers to any sum of scalar multiples of vectors, and the span denotes the set of all these vectors that can be written as this linear combination. So the most common way to generate a subspace is by using the span of the set of vectors. And this brings us to Theorem 1. Theorem 1 is basically the basis of your homework, and it will be utilized a lot in your homework and referred to a lot in your homework. And basically this is saying if we have this set of vectors, then the span of those vectors is a subspace of V. Okay? So let's see this in action. So it says, let H be the set of all vectors of the form given to you here, where A and B are just scalars, just random arbitrary scalars. And I have written H as the set here, we want to show that H is a subset of R4. And what we want to do in order to do that is we want to first write H as column vectors. So I can write this, I can write H as A minus 3B, B minus A, and B. Well, writing this as column vectors, the first thing I can do, which is something we've done previously, is I can factor out an A and then write the coefficients of A. So 1, -1, 1, and 0. And this represents V1. I can do the same thing by factoring out that GCF, if you will, of B. So then writing those coefficients, I'd have -3, 1, 0, and 1. And this would be vector 2. So this here shows, that H is the span of vector 1 and vector 2. So, or thus, H is a subspace of R4, and this is by theorem 1, which we just discussed. Now this wraps up what I want to show you for this section. I think that this might be one of those sections that you might want to take some time to read if you have not yet already. Take some time on this section and dig deep. Good luck.